Excellent. We've covered the prerequisites, so we've looked and seen how decision trees work and how bootstrap sampling work. We could use both of those ideas together to understand how a random forest algorithm works. The big idea about random forests is let's build a bunch of decision trees, each one being very different than every other decision tree, and let's combine them. So a random forest is simply a combination of very different and very individually terrible decision trees. But we find when we combine them all into one model, we create a very, very good model. So here's how it works. Let's say we want to create a random forest with 10 decision trees in it. So 10 trees are in this random forest. To create the first decision tree, you take a bootstrap sample of the data. So we saw how we did that. We take a sample of the data with replacement. Then we have to split this data to make the first split of the decision tree. When we're splitting the data, we start by randomly selecting only a subset of the total amount of variables you have. And you might ask, well, why don't we just use all of the variables each time like we did in a decision tree, iterating through every variable and finding the one that has the best possible split? Well, by randomly selecting some variables, you ensure that every single tree looks very different. So in the example on decision trees, we had 3 variables. We were assessing age, gender, and years of experience. In a random forest, we would only take a subset of those. So maybe we'd only randomly select 2 of them, like age and gender. We would ignore years of experience in the first split. And this is where the word random comes from, the bootstrap sample of the data and randomly selecting some variables. But with each of those 2 variables, now you follow the exact methodology of your decision tree, where for that first split, you find which of those 2 variables you randomly chose produces the best split in your data. Then you have 2 more nodes. And now we're in step 5, actually. So we just did step 3 for each variable selected, find the split point which minimizes mean squared error, or the difference between these 2 buckets. We did step 4, you split the data using the variable with the lowest MSE. And then step 5, you repeat steps 2 through 4 for every single node. And so we saw we split the data one time. Now we look at the very first split point, and we randomly select 2 more variables, in this case from your data set. So maybe this time you randomly select years of experience and gender. You only consider those 2 variables and the possible splits on those for this next splitting decision, and so on. So each time you have to split your data set further and further, you select a random new 2 variables. And you do this until you've built your entire tree, which means you've either run out of data or you reach some other stopping condition that you've defined ahead of time. And then that's how you build your first tree. And then you repeat this process to build 9 more trees, so you have 10 decision trees in your forest. And when you're done with that, you've completed your random forest. To make a prediction with this model, with this random forest model, you take an observation and you run it down each one of these trees. So you have each one of these 10 trees make a prediction on what it thinks the average income is of this individual. And then you take the average income prediction from every single tree and you average them all together. And that's how you determine your final prediction. And it's that final prediction that tends to beat every other model.
So you can stop there. That'd be good. Okay.
Next, we're going to cover the most important parameters in your random forest model. You'll remember that a machine learning algorithm can be viewed like a black box, where you have inputs that go into the black box, namely your data set and the labels on your data set, or the values of your observations, the y variables. So the y variables and x variables go into this black box, and outside of this black box, or the black box produces outputs or predictions. But there are also knobs on the black box. So there are different settings you can do. So this random forest is like a black box, and here are the most important settings for it, the ones that you need to know. There are two main types of parameters. There are parameters that make your model better. So these will make things like your AUC higher, or your R-squared value higher, or your accuracy higher. And then there are parameters that will make it easier to train the model. So this will just make it faster, or make the training more elegant and more robust. And we'll cover each one of them. So I'll briefly touch on each one right now. The parameters that will make your model better are the number of estimators. These are the number of trees in your forest. So if you have 100 trees in your forest, your model performs better than if you only have 10 trees in your forest. Max features. This is how I said that a random forest at every single split point only takes a subset of the total variables available to you. So let's say you have a really big data set with 100 variables in your data set. Well, by defining max features, it says how many of those 100 variables should be randomly chosen to define the split point, or to possibly make the split point. So if you were to make the max features equal to 0.9, well then at every single split point it would randomly select 90 of the variables. If you make it auto or none, it uses all the variables, so it just essentially builds a decision tree. If you put square root, it does the square root of 100, so it just takes 10 observations every single split point, and so on. So you have different options there for max features. And then the final parameter that we will want to test is the minimum number of samples per leaf. So you'll remember that a decision tree will just keep splitting this data. It'll keep splitting it over and over and over and over until it's exhausted all of the data, until each end node only has one observation in every single end node. Well, by defining this, we could say, let's stop if there's 3 observations in an end node. Let's not continue to split until you have one lone sample in a final end node of your decision tree. So what I found with this one is it's best to try 1, 2, and 3 samples in your final end node, and if 3 is the best, try higher numbers. Parameters that you'll see that'll make it easier to train your model. There's this nJobs parameter. By setting it equal to -1, you use all of the processor cores on your laptop. There's the random state parameter. By setting it equal to a value, a constant value, it'll make your work repeatable. So anybody will be able to take your model and get the exact same answers. Remember, random forests are built on randomness, and so if there's no way to control that randomness, or to at least predefine what random series of numbers we'll be using, all of our models might be slightly different. And so by setting random state equal to something, your answers will be identical to my answers. And then finally, there's out-of-bag scores, or OOB score. These are amazing. These are incredible. It's Random Forest's custom validation method. They're called out-of-bag predictions, and it could be compared to when you have a holdout sample. So when you hold out 20% of your data and test your model on that 20%, how you're able to ensure you're not overfitting to your data set, and you're able to generalize how accurate will this model be on new unknown data. Random forests have their own method, and we'll cover that right now because it is very incredible how it works. Out-of-bag predictions. You'll remember that about 1/3 of observations don't show up in a bootstrap sample. Because you'll have repeated observations in your bootstrap sample, that means there has to be some observations that are left out. Because an individual tree in the forest is made from a bootstrap sample, it means that about 1/3 of the data was not used to build that tree. So we could track which observations were used to build which trees in your data set. And this is where the magic comes into play. After you train your random forest, we're able to see which observations were used to build which trees. And then what we could do is we could say, let's run that observation, or any observation, through all of the trees or that observation wasn't used when you were building the tree. So what it does is it's almost as if that observation didn't even exist in your data set because that observation wasn't used to build those trees in your random forest. And so it gives you a very fair assessment by just using those trees to predict that observation. It gives you a fair assessment of how your entire model will predict an observation like that in the future. So what out-of-bag predictions are similar to? They're similar to something that's also incredible and also awesome, but it's a very computationally expensive method. So let's read through this. Imagine if we were to train a model with in estimator's trees. So we were to train it with 100 trees. But each time we trained the model, we excluded one observation from our data set. Let's say we have a data set with 1,000 observations in it. So we set out one of those observations. And then we train this model, then use the trained model to predict the excluded observation. And then record the prediction. So how accurate were you in that prediction? And then we repeated this for every single observation in the data set. So we essentially repeated this process 1,000 times, predicting what we think the value of every single observation was after leaving it out and training the entire model. And then we were to collect all of these final predictions. These final predictions are going to be similar to your out-of-bag prediction errors. So that very, very computationally expensive procedure can be done in random forests in one pass incredibly fast. This complex method, the one I just described that takes 1,000 iterations, takes tremendously longer than the out-of-bag estimates takes to run. So what we could see here is that we could calculate it, and you could read this if you want, and if you have any questions, ask Mike, he'll answer them for you. It actually, by doing this difficult computationally expensive method, it'll take the number of observations you have in your data set divided by 3 times longer to train to test this model. So if you have 1,000 observations in your data set, it's going to take 1,000 divided by 3 times faster to train than the leave one out method, or excuse me, than the out-of-bag method. So the key takeaway of this is we're going to be using out-of-bag prediction errors going forward because they give us a very, very precise look at how generalizable our model is. And it's very fast.